Chapter 5 starts out with a section on eigenvectors and eigenvalues. And this is going to be the topic or the motivating topic for all of Chapter 5. So what we're going to do is we're going to start just multiplying a matrix times a vector and seeing what we get out. So just push pause and multiply this matrix A times this vector X. All right, so when I do that, 4, 9, 2, 1 multiplied times the vector 3, 1. 4 times 3 gives me 12, plus 9 times 1 gives me 21. And then 2 times 3 gives me 6, plus 1 times 1, which gives me 6 plus 1 is 7. Okay? Now, what do we notice about this? Hopefully, you noticed that this 21, 7 is simply a constant multiple of the vector 3, 1. In other words, this 21, 7 is actually 3, 1, the vector 3, 1, multiplied by 7. So with this matrix and this vector, when I multiplied the matrix times the vector, I ended up with just 7 times that original vector. Now, obviously, this case was unique, so I'd like you to try the same thing. See what happens when you multiply that same matrix A times the vector negative 3, 2. And then also try to multiply that matrix A times the vector 1, 4. So negative 3, 2 and 1, 4 are the two vectors I want you to multiply. Push pause on the video and go ahead and do that. All right, so hopefully you did both of those. Now, when I did those, what's happening, um, obviously I just did the multiplying the matrix times 3, 1. Now let's multiply the matrix times the vector negative 3, 2. When you do that, 4 times negative 3 plus 9 times 2 gives you a positive 6. 2 times negative 3 plus 1 times 2 gives you a negative 4. And notice that the matrix, when I multiplied times negative 3, 2, gave me out basically the same thing, well, exactly the same thing as taking the constant negative 2 times my vector. Okay. Now this matrix, obviously these first two examples show you that sometimes you multiply a vector by a matrix and it's a scalar multiple of that vector. In this case, we had a 7 times the vector. In this case, our scalar was negative 2. But obviously, that's not going to be true for every vector. And that's what the example using the vector 1, 4 hopefully showed you. We had the matrix times 1, 4. You get out 46. And that is 46 is clearly not a scalar multiple of the vector 1, 4. So there's going to be some vectors out there for this matrix which are scalar multiple, in which the matrix multiplication acts as a scalar multiple of that particular vector. And there's going to be other vectors where when I do the matrix multiplication, it is not a scalar multiple of that original vector. And this is the concept of eigenvectors and eigenvalues. So we say we have an eigenvector of a usually square matrix. In fact, always has to be square, excuse me. It's a vector such that when you multiply that vector times a matrix, you get out just a scalar multiple of the vector itself. This symbol here, that scalar, is called lambda. It's a Greek letter lambda. That's what we always use for eigen vectors. And that constant number lambda is going to be some real number for the most part of chapter 5. And that lambda is an eigenvalue. All right. So eigenvectors and eigenvalues kind of come in as a pair. The eigenvector is associated with a particular eigenvalue, and the eigenvalue is associated with particular vectors. All right. So what we can do is we can determine if the vector is an eigenvector of a certain matrix. How we do that is we just multiply the matrix times the vector, and we see if that multiplication would have resulted in me multiplying a constant times the vector. So why don't you go ahead and try that. See if this matrix A and this matrix, excuse me, let me restate that. See if this vector X is an eigenvector for matrix A. Okay, so I'm going to do that. Let's take my matrix 5, 2, 1, 6, multiply it times the vector negative 4, 2. When you do this, 5 times negative 4 is negative 20, plus 2 times 2. I got a negative 16. 1 times negative 4 is negative 4. 6 times 2 is 12. So negative 4 plus 12 becomes an 8. So the question is negative 16, 8 a multiple of negative 4, 2? All right, it is. We can take negative 4, 2 and multiply that by 4. So in this case, our lambda, our eigenvalue, is going to be 4. Okay, so yes, negative 4, 2 is an eigenvector, and moreover, it has eigenvalue of 4. I'd like you to try to calculate, see if 6, 1 is going to be an eigenvector. If it is, find the eigenvalue. And then also, I want you to check if 5, 5 is an eigenvector. And if it is, find the eigenvalue. So try to find if 6, 1 is an eigenvector and if 5, 5 is an eigenvector. Go ahead and push pause and do that. When I calculated these two multiplication problems, so when I looked at the matrix A times vector 6, 1, and then I looked at matrix A times the vector 5, 5, what I found was that when you multiply my matrix times 6, 1, I ended up with 32, 12. In other words, the vector 32, 12. And notice that is not a scalar multiple of the vector 6, 1. So in this case, we would say the vector 6, 1 is not an eigenvector. at least not for this matrix. All right. By the way, again, the other one, yes, 4, -2 was an eigenvector with eigenvalue of 4. That's what we would have said. How about this? Well, when you go off to 5, 5, when you multiply my matrix A times 5, 5, I get 35, 35, which is just 7 multiplied times 5, 5. So 5, 5 is an eigenvector. So that vector right there is an eigenvector. For the matrix A. And moreover, it has eigenvalue of 7. All right, so the eigenvector 5, 5 has an eigenvalue of 7. Now, we're going to make some observations here. And so I want you to do 2 more calculations with this matrix. I want you to calculate what's going to happen. Whoops, just one more calculation, excuse me. I want you to see what happens when you multiply the matrix A times the vector 2, 2. Push pause, go ahead and do that, and then just see what happens. All right, hopefully you went ahead and did that. And what we'll see, let me copy that equation, is that if I take my matrix, my apologies there, and multiply by the vector 2, 2, 5 times 2 is 10, 2 times 2 is 4, so 10 plus 4 is 14. 1 times 2 is 2, 6 times 2 is 12, so 2 plus 12 is also 14. Notice that what we came up with is, again, 2, 2 is an eigenvector whose eigenvalue is 7. Now, 5, 5 was also an eigenvector whose eigenvalue is 7. And if you observe, 2, 2 is actually just some multiple. It's 2/5 multiplied times the vector 5, 5. Okay? So if you take 2/5, multiply it times 5, 5, you get out the vector 2, 2. So when we have scalar multiples of eigenvectors, the scalar multiple is also going to be an eigenvector with the same eigenvalue. All right? So that should be our observation here. If we have an eigenvector which we call x of the matrix A, and that eigenvector has eigenvalue of lambda, then any scalar multiple of x will also be an eigenvector of A with the exact same eigenvalue. Now, I could have proved this in the previous example, but I'm going to prove this in a more general sense. And these are the types of proofs you should expect, if you're going to be tested on. So how could we show if x is an eigenvector of A with eigenvalue lambda, then C of x is an eigenvector of A with eigenvalue lambda as well. We start with the if part. We're going to start by assuming that x is an eigenvalue of A with eigenvalue of lambda. What that means is that A multiplied times vector x is equal to lambda times vector x. Okay, these are going to be vectors, so I'll make those bold. Now, if that is true, then notice what's going to happen when I multiply A times a constant times that same vector. So if I take this constant times a vector and multiply it by A, well, what do I get? Matrix multiplication along with multiplication of a constant. We've seen this property before, that we can pull the constant out in front of A. All right? So we can take C times AX. We can utilize the fact that scalar multiplication is commutative, and the fact that scalar multiplication along with matrix multiplication is associative. So we pull the C out front, regroup. Well, A times X, that's just simply lambda times X, right? So I'm going to take this lambda times X. We know we can substitute it for AX. So that has to be C times lambda X, which again, these are just two scalars. Lambda and a constant C are scalars. So they commute and are associative. So we can see that when I multiply A times a scalar times that vector, it gives me lambda times the same scalar times the same vector. Okay? So this shows that Cx is also an eigenvector with eigenvalue lambda. All right? Oops, excuse me, Cx is an eigenvector of A with eigenvalue lambda. So that's the proof of that observation. Now you can go further here and, excuse me, also think about what's happening in a broader sense. So let's say lambda is an eigenvalue for a matrix. It turns out we can collect all of the eigenvectors that are associated with that eigenvalue. So in my instance, we had 5, 5, and 2, 2. It turns out 1, 1, 4, 4, 17, 17 would have all been eigenvectors in, and is associated with eigenvalue 7 for this matrix. So if I give you a matrix and I give you an eigenvalue, there's going to be lots of vectors, hopefully, with the same eigenvalue. That set of all of these vectors, all the vectors that look like this, is called an eigenspace of the matrix corresponding to eigenvalue of lambda. All right. And it turns out the eigenspace is a subspace. So it's a subspace of whatever Rn that I'm in. So whatever vector space that I'm in, my eigenspace is going to be a subspace of that vector space. Let me prove to you that the eigenspace is in fact a subspace. In order to show that the eigenspace is a subspace, we're going to need to show the three properties of a subspace. First, that it contains the zero vector. Second, that our space or set is closed under addition. And third, we're closed under scalar multiplication. All right, so we're going to say this is going to be the eigenspace for matrix A with eigenvalue lambda. All right, so that's what we're going to do. And we're going to assume, just like we always do, that, well, let's do this one by one. So first off, contains the zero vector. All we have to say is that if you take any matrix A, you multiply it times the zero vector, do you in fact get lambda times the zero vector? And you say, well, of course, zero vector times zero vector, zero vector. When I multiply it times A, gives me the zero vector, which is the same thing I get when I take lambda times the zero vector. All right, so basically, the zero vector has to be in there because the zero vector, when you multiply it either by a matrix or by a scalar, gives you the zero vector. All right, so therefore A times the zero vector is equal to lambda times the zero vector. So yes, my eigenspace contains the zero vector. All right, closed under addition. So per the usual, we let x and y, no, let me do this, x and y, goodness, be vectors in our eigenspace. All right, let's see what multiplying the matrix A times the sum of x plus y does. We've done this trick before. Matrix A times x plus y, we can distribute ax plus ay. Now, I didn't bold these, but they're supposed to be vectors. There's a few times I did that on the notes as well. So there you go. Now, what's it mean to be in the eigenspace? Well, it means that A times x is the same thing as lambda times x. And A times y is the same thing as lambda times y. Where again, lambda is just the constant eigenvalue. So if I factor out a lambda, what we see is that when you take A times the sum of any two vectors, you get the same thing as taking the eigenvalue times the sum of any two vectors. So as long as two vectors have the same eigenvalue, then we can do that. So what's that mean? That means the vector sum, x plus y, is in the eigenspace. So therefore, we are closed under addition. Now, oops, sorry about that. Getting pop-ups. So we're closed under addition. How about closed under scalar multiplication? We'd let x be in our eigenspace. Something's off there. So we let x be in the eigenspace. And this is actually what we just did. If you remember, what we showed is that if we have our matrix A multiplied times a scalar multiple of x, then it's the same thing as taking lambda times a scalar multiple times x. Therefore, any scalar multiple is an eigenvalue of A with eigenvalue, an eigenvector of A with eigenvalue lambda. That's another way to say scalar multiple of x is in the eigenspace. All right. So we have the three properties of subspaces. We have closed under scalar multiplication, closed under addition, and containing the zero vector. And this shows that an eigenspace is a subspace regardless of which A and which lambda we choose. Now the next type of problem in 5.1 asks, is a certain value, is lambda equal -2, for instance, an eigenvalue for the matrix? If so, can we find an eigenvector? Now this one's a little bit trickier than the last one. Is when we were given a vector, all we had to do was multiply A times that vector and kind of look and see, is that a scalar multiple of the original vector? If I'm given a value, I have to think a little bit differently. So here's what we do. If we have an eigenvector with a certain eigenvalue, we'll call it, again, eigenvector x with eigenvalue lambda, then this is true. A times x has to be the same as lambda times x. Now, I can move things around because this is just a vector equation. So I can move things around to the other side. We have a matrix equation, vector equation, however you like to write it. So we could subtract lambda x from both sides and end up with a times x minus lambda x equals 0. Well, a scalar times a vector is the same thing as the scalar times the identity times the vector. So we're saying, is there a vector which this happens to? If there is such a vector that happens to, then a minus lambda I multiplied that times that vector is going to give me the 0 vector. Now, if I want a non-trivial solution to this, if I want my x to be something other than the 0 vector, then that's going to force this matrix equation to have a free variable in it. All right, so I have a homogeneous matrix equation. This thing is just a minus lambda I, is just a fancy matrix, times a vector equals 0. So if I'm looking for non-trivial solutions, I need to have a minus lambda I have a free variable. And so that's all I have to do. I have to rethink this, and I have to think through what's happening in a minus lambda I. So let's go back to the problem I just had. We were looking if -2 was an eigenvalue for this matrix. And if it was, find the eigenvector. All right, so let's go through this. We have our matrix. We have our lambda that we're going to check and see if it's an eigenvalue or not. So ax equals lambda x is equivalent to this equation. So we're just needed to create this matrix, A minus lambda I, and then see if we can find a solution to this homogeneous matrix equation. All right. Now, the first thing I want to do is just set up what A minus lambda I is. Okay. In this case, obviously our lambda is -2. So we're going to do A minus -2I. I'm going to rewrite that as A plus 2I. Okay? Now, if you think about, we know what A is. I'll write out all the steps here. So we know A is a 2 by 2 matrix whose entries are 4, 2, 18, 4. We're going to add 2 times the identity. Again, this is the 2 by 2 identity matrix. Otherwise, it wouldn't make sense to add. If we were in the 3 by 3 case, we do that. So A minus lambda I is going to be the sum of 4, 2, 18, 4 with 2, 0, 0, 2. So you'll notice what kind of a matrix we get. We get a 2 by 2 matrix. Hopefully this doesn't wrap me around, but it did. And what it's going to give me is 6, 2, 18, 6. All right? So what we're looking for is we're looking to see if this homogeneous system, or excuse me, this homogeneous matrix equation has a solution, which basically is asking me, does six, 2, 18, 6 times of, it's going to be a 2 by 2 vector, equaling the 0 vector, does that thing have a solution, and in particular, a non-trivial one? All right, so all we have to do is row reduce this. So put A minus lambda I in row reduced echelon form. We've done this so many times, I don't think we need to go over it again. Forgot my B. There we go. So A minus lambda I, and what you're going to get when you do that, well, we can do that. I guess we can go over it once. Go into our calculator. Into my matrix. I'll edit. So I want a 2 by 2 matrix. And my entries are 6, 2, 18, 6. Go back to the home screen. Put that using the matrix menu, math, row reduced echelon form. and you'll get 1, 1/3, 0, 0. Okay? So the row reduced echelon form of this 2 by 2 matrix is 1, 1/3, 0, 0. And yes, this does have a free variable. Okay? So yes, -2 is an eigenvalue. Moreover, the eigenvector is going to be this x, which is just some solution to this homogeneous matrix equation. So what we can do is we can say, well, what eigenvectors are going to work there? And it's pretty obvious that x1 has to be negative 1/3 of x2. And by that, what I'm trying to get out is, my apologies. Um, Let me restate this. I apologize. So x1 I'm thinking is the first entry, x2 is the second entry. If I look at this solution homogeneous, we'd say x1 plus 1/3 times x2 equals 0. So x2 is a free variable. I'm just going to let that be 1. x1, well, if I let x2 be a free variable, x1 has to be negative 1/3. All right, so there you go. So yes, -2 is an eigenvalue. Here is one eigenvector. And obviously, any multiple, any scalar multiple of that is also an eigenvector. So if you chose a different value for your free variable, again, my free variable is x2. If I choose a different value for my x2, you can just figure out what x1 has to be. All right. Hopefully that all makes sense. So that first top line here tells me x1 plus 1/3 x2 has to be 0, which means x1 has to be negative 1/3 x2, and x2 is free. Again, I'm writing out the general solution. So let x2 be anything you want, and then x1 has to be negative 1/3 of that. I let x2 be 1, so x1 has to be negative 1/3 of that. Okay, that was a little bit longer than it needed to be, but there you go. All right, so -2 is an eigenvalue, and we found an eigenvector for that. I want you to take a second and try to see if 4 is an eigenvalue for that matrix. If it is, let us know. And then also see if 10 is an eigenvalue for that matrix. So we have two questions. I want you to pause and do it to see if 4 is an eigenvalue and see if 10 is an eigenvalue for that same matrix we dealt with in the previous example. Okay, so I'm going to do both of those. Hopefully you did those. I'll do them. I'll go through them pretty quickly. Okay, so let's start with 4. All right, so if we have lambda equals 4, what we do is we go a minus lambda I times x equals 0. Same thing, homogeneous matrix equation. In this case, I take a minus 4 times the identity. Now, once you get good at this, you'll see that the only numbers affected are the diagonals. So when you subtract 4 from the identity. So I'm going to subtract 4 from the 1, 1 spot, and I'm going to subtract 4 from the 2, 2 spot. So what that'll do, 18 and 2 will be left alone. 4 minus 4 is 0. 4 minus 4 is 0 there. So we get that. Now, if you row reduce a minus 4 times the identity, what you'll get is the identity matrix. And what that means is that the only solution to this equation when I have lambda equals 4 is the trivial solution. And therefore we say that lambda equals 4 is not an eigenvalue of the matrix. Now, this does bring up one interesting fact, okay? When we established the concept of eigenvalues, we said that an eigenvalue is something where I can find a vector, which we called an eigenvector, which did this. But there is a caveat. So an eigenvalue of a matrix, we have to have a non-zero vector do this. Let me explain that again. This equation is always true when I'm dealing with zero vectors. Okay? So it's a trivial thing to say that 0 is an eigenvector with eigenvalue 4. So 4 is not an eigenvalue because of the vector 0. To be a proper eigenvalue, you have to have a non-zero vector satisfy this equation. All right, so we kind of throw out the trivial case with 0, and we say lambda equals 4 is not an eigenvalue because there's no non-zero vector that satisfies this equation. Now, when we do the same calculation with lambda equals 10, here's what happens. So we go a minus 10 times the identity. So we're going to subtract 10 from the 1, 1 spot. That'll give me a negative 6 there. Subtract 10 from the 2, 2 spot. That'll give me a negative 6 there. So a minus 10 times the identity is negative 6, 2, 18, negative 6. When you row reduce that equation so that you can solve the homogeneous system, you get 1, negative a third, 0, 0. Now this is very similar, don't get confused. In the previous problem we had a positive 1/3 there. When I look at the general solution is x1 has to be equal to positive 1/3 x2, and x2 can be free. And so yes, in fact, lambda equals 10 is an eigenvalue, and moreover, one eigenvector is 1/3 1. If you remember, for our lambda equals -2, -2 was another eigenvalue. It had eigenvector -1/3 1. All right, so just reiterate, -2 was an eigenvalue for the matrix, and the eigenvector was -1/3 1. 4 was not an eigenvalue. 10 is an eigenvalue, and it has an associated eigenvector of 1/3 1. Okay. So that's it. That's how to find if a certain number is an eigenvalue for a certain matrix. Now let's think about the implications of this for triangular matrices. So if I didn't know a specific lambda, or if I wasn't given one, could I find the eigenvalues of a particular matrix, like this one? So we have this matrix 6, 4, -9, 0, 5, 11, 0, 0, -3. It's obviously a triangular matrix. Think about what the eigenvalues would have to be. Now let's think about how we would show that. We think about this situation. We have our A, we have our lambda. We want to take A minus a certain particular value of lambda times I, multiplied all that by some arbitrary vector and get 0. And we hope that when we do that, we end up with some free variables. Okay? Now let's create A minus lambda I and see what happens. So we have 6, 4, -9. So I'd do 6, 4, -9, 0, 5, 11, 0, 0, -3. And that's my A. So if I subtract lambda times I, what I would do to each of the diagonal entries, all I'd have to do is subtract lambda. Oops. All right. Now, when is this going to have free variables? When I row reduce this, well, think about this. It's already triangular, so this is all zeros. How am I going to get free variables? Well, I'm going to get a free variable if this entry is 0. Okay? So in other words, I get a free variable when lambda is 6. Because if lambda is 6, then this column becomes an all zeros column, and I get a free variable. Well, another way I could get a free variable is if this entry is 0. So if 5 minus lambda is 0, notice I can't have a pivot position in the 1, 1 spot. So when lambda is 5, this becomes 0. And so this matrix has a free variable when lambda is 5. And also, notice what's going to happen. When lambda is -3, I'm going to get a 0 here, which gives me a whole row of zeros. And so when lambda equals -3, I also end up, let me see if I can get that, yep, with a free variable. Now it turns out, so those values for lambda give me non-trivial solutions to the homogeneous matrix equation. And what that means is that those values for lambda are going to be eigenvalues for my matrix. So these three values, lambda equals 6, lambda equals 5, lambda equals -3, are all eigenvalues for my matrix. By the way, if we wanted to, we could find, a vector for each of these eigenvalues that worked, and those types of things. So hopefully that makes sense. Now, notice what's unique about 6, 5, and negative 3. Because, 6, 5, negative 3 popped out because they were the diagonal entries in our 3 by 3 matrix. And so because this matrix was triangular, 6, 5, negative 3 became eigenvalues. Now notice that is not the case if, for instance, this number were a 7. If this number were a 7 here, if the 2, 1 entry were a 7, all of that stuff gets thrown out. So this is the diagonal entries being the eigenvalues only works when we have a triangular matrix. In fact, you can figure out from the last example we saw that 10 was an eigenvalue, and that's obviously not on the diagonal. So when I have triangular matrices, the diagonal entries are going to be my eigenvalues. And that is one of the theorems that is in the book. So the eigenvalues of a triangular matrix are the entries of the main diagonal. All right, so I want you to use this fact to find the eigenvalues of this matrix. And once you find the eigenvalues, I want you to go ahead and row reduce A minus lambda I and find an eigenvector for each of the eigenvalues you get. This eigenvector will form a basis for the eigenspace. All right. So I want you to go ahead and do that for this matrix. Find the eigenvalues, and then for each of the eigenvalues, come up with an eigenvector. Okay, so hopefully you went ahead and did that. It will take you a little bit of time if you're getting discouraged. Hopefully you aren't. So let's go through this. So we have 2, 3, 4, 0, 1, 8, 0, 0, 3 as our matrix. Now because this is a triangular matrix, I know that the 3 eigenvalues are going to be 2, 1, and 3. All right, because those are the diagonal entries of my triangular matrix. So lambda equals 1, lambda equals 2, and lambda equals 3. I don't need to do that much. Are the eigenvalues. So 2, 1, 3. Now, for each eigenvalue, I'm going to try to solve this equation, this homogeneous matrix equation. So I'm going to take A minus, well, I have to do one at a time. So let's start with 2. So let's go A minus 2I. So start with lambda equals 2. A minus 2I, we take A and subtract 2 from the diagonal entries. So the diagonal entries will now be 0, -1, 1. When you put that into your calculator and put that into row reduced echelon form, you end up with this matrix. Now what this matrix symbolizes is that your variable x1 is free, your variable x2 has to be equal to 0, and your variable x3 has to be equal to 0. That is, if x1, x2, x3 are the three entries in my vector x. All right, so x1, x2, x3, I'm imagining are the three entries for vector x. And in order for that homogeneous equation to be true, x1 has to be free, x2 would be 0, x3 would be 0. And therefore, 1, 0, 0 is an eigenvector corresponding to eigenvalue of 2. And because I only have one free variable, that vector actually forms a basis for the eigenspace corresponding to eigenvalue of 2. Now we can do the same thing with lambda equals 1 and lambda equals 3. In fact, we will. If you haven't done that before, if you want some practice, push pause and try to do that on your own. Otherwise, I'm just going to keep going. So for lambda equals 1, I go a minus lambda I, so I subtract 1 from the diagonal, 1 from each of the diagonal entries. We're going to get this matrix. When you row reduce that matrix, you get 1, 3, 0, 0, 0, 1, 0, 0, 0. Now notice what this one does. If I were looking for a general solution, x1 would be equal to negative 3x2. That's because x1 plus 3x2 has to be equal to 0. So you move the 3x2 to the other side. And then x3 would have to be equal to 0. So x1 is equal to negative 3x2. x2 is my free variable here. And then x3 would have to be 0. Now, what that means, since we only had one free variable, we're going to have one vector in the basis for the eigenspace. And that vector would be negative 3, 1, 0. Now, I hope that you've caught on that what this eigenspace is, this eigenspace is just a set of vectors which gets mapped to the 0 vector for this matrix. So the eigenspace is actually just the null space of that matrix. By the way, that's another way to prove that the eigenspace is a subspace, because the eigenspace is just the null space for this matrix here. All right, so let's do the last eigenvalue, the eigenvalue of 3. Let's find a basis for the eigenspace where the eigenvalue is 3. So just like before, we go a minus 3 times our identity. When I do that, I get negative 1, negative 2, and 0 as the diagonal entries. I'm looking for the null space of this matrix. The null space of this matrix is going to be the eigenspace of A with eigenvalue of 3. So I'm going to row reduce A minus 3i. I came up with this, 0, 1, negative 16, 0, 1, negative 4, 0, 0, 0. Which general solution would say x1 minus 16x3 equals 0, x2 minus 4x3 equals 0. And what that means is that x1 would have to be equal to 16x3, x2 would have to be equal to 4x3, and x3 could be free. So one free variable here, basis for the null space of A minus 3i is the basis for the eigenspace corresponding to lambda equals 3. and we get 16, 4, 1 as the vector, or a vector, which forms a basis for the eigenspace of A corresponding to lambda equals 3. I hope that all makes sense. All of those calculations, all right? Now, notice that we had each of these vectors, when we found a basis for the eigenspace, each eigenspace was of dimension 1. It only had one vector in each of the bases. That's not always true, but we'll see some properties of that. Now, the other thing I want to point out about the eigenspace and the eigenspace vectors can be shown if we look at those basis elements, or excuse me, the elements, the vectors in each basis, all sort of together. So let's go back and let's collect all the vectors that we had. So with eigenvalue of 2, we got the vector 1, 0, 0. With an eigenvalue of 1, we got the vector negative 3, 1, 0. And with an eigenvalue of 3, we got the vector 16, 4, 1. So let's collect all those together. I did that here. 1, 0, 0, negative 3, 1, 0, 16, 4, 1. I want you to notice that these are if I created a set, if I formed a set of these three vectors, they would be linearly independent. In fact, they'd be linearly independent, and because I have three of them, they would form a basis for R3. Now, you don't always get as many you don't always get enough vectors, but it turns out that if I have a bunch of eigenspace bases and I sort of throw all of those vectors into one big set, all of those vectors will be linearly independent. All right? And so here's the thing. If V1 and V2 and V3 and all the way up to VP are all each an eigenvector that correspond to different eigenvalues, so like in our case, the vector 1, 0, 0 corresponded to the eigenvalue of 1, eigenvalue of 2, the vector negative 3, 1, 0 corresponding to the eigenvalue of 1, and the vector 16, 4, 1 corresponded to the eigenvalue of 3. So if we have eigenvectors and they correspond to different eigenvalues, then the set of those eigenvectors has to be linearly independent. Now, like I said, in our case, we had, because there were three of them, those three vectors formed a basis. But in general, you don't always get three eigenvectors corresponding to three different eigenvalues. So all we can say right now is that if you have a couple of vectors, a few vectors, and each of them has a different eigenvalue, then the set of those vectors will be linearly independent. That's going to be a really important property when we move forward. So with this matrix A, I had 3 different eigenvalues. Each of those eigenvalues corresponded to a different eigenvector, and the set of those 3 eigenvectors was linearly independent. And that's it. So in the next section, we'll continue on the idea of eigenvectors and eigenvalues, and we'll ask ourselves, well, how can we find eigenvalues in general? If I don't have a triangular matrix and I can't use the fact that they're the diagonal entries, how could I find, for instance, eigenvalues here if I'm not given a few numbers to try? All right, so that's what we're going to look at next time.